Hello, I believe we are live. Okay, why is the image so dark? Okay, I think it's fine now. So, welcome to day 10 of learning OpenGL. Today's topic is lightcasters. After we did the materials and the lighting maps, we implemented the diffuse map and the specular map, and we got a result similar to this. Let me just go back and see where we are. Okay, yeah, there we go. So we have the directional light working, we have the diffuse map and the specular map that you can see right here. Okay, let's begin our new topic. Lightcasters. All the lighting we've used so far came from a single source that is a single point in space. It gives good results, but in the real world, we have several types of light that each act different. A light source that casts light upon objects is called a lightcaster. In this chapter, we'll discuss several different types of lightcasters. Learning to simulate different light sources is yet another tool in your toolbox to further enrich your environments. We'll first discuss a directional light, then a point light, which is an extension of what we had before. And lastly, we'll discuss spotlights. In the next chapter, we'll combine several of these different light types into one scene. Okay, so he's saying we'll discuss directional light. Okay, the one that we had was actually a point light. Okay, direction light. When a light source is far away, the light rays coming, excuse me, the light rays coming from the light source are close to parallel to each other. It looks like all the light rays are coming from the same direction, regardless of where the object and or the viewer is. When a light source is modeled to be infinitely far away, it is called a directional light. Since all its light rays have the same direction, it is independent of the location of the light source. A fine example of directional light is the sun as we know it. The sun is not infinitely far away from us, but it is so far away that we can perceive it as being infinitely far away from the lighting calculations. All the light rays from the sun are then modeled as parallel rays as you can see in the following image. Because all the light rays are parallel, it does not matter how each object relates to the light source's position, since the light direction remains the same for each object in the scene. Because the light's direction vector stays the same, the lighting calculations will be similar for each object in the scene. We can model such a directional light by defining a light direction vector instead of a position vector. The shader calculations remain mostly the same, except this time we directly use the light's direction vector instead of calculating the light dir vector using the light's position vector. Okay, so direction light is actually even simpler than the point light, because now we don't have to calculate this light dir, which is the vector coming from the position of the light source to the object. Because all the rays are parallel, that means this direction vector is not going to change. So that's that. Note that we first negate the light dot direction vector. The light calculations we use so far accept the light direction to be a direction from the fragment towards the light source, but the lighting calculations we use so far expect the light direction to be a direction from the fragment towards the light source, but people generally prefer to specify a directional light as a global direction pointing from the light source. Therefore, we have to negate the global light direction vector to switch its direction. It's now a direction vector pointing towards the light source. Also, be sure to normalize the vector, since it is unwise to assume the input vector to be a unit vector. The resulting light vector is then used as before in the diffuse and specular computations. To clearly demonstrate that a directional light has the same effect on multiple objects, we revisit the container party scene from the end of the coordinate systems chapter. In case you missed the party, we defined 10 different container positions and generated a different model matrix per container, where each model matrix contained the appropriate local to world transformations. Yeah, I remember doing that, and then we removed it. Also, don't forget to actually specify the direction of the light source. Note that we define the direction as a direction from the light source. You can quickly see the light's direction is pointing downwards. We've discussed passing the light's position and direction vectors as vec3 for a while now, but some people tend to prefer to keep all the vectors defined as vec4. When defining position vectors as vec4, it is important to set W component to 1, so translation and projections are properly applied. However, when defining a direction vector as a vec4, we don't want translations to have an effect since they just represent directions, nothing more. So then we define the W component to be 0. Direction vectors can then be represented as a vec4, and here the W component is set to 0. This can also function as an easy check for light types. You can check if the W component is equal to 1 to see that we now have a light's position vector, and if W is equal to 0, we have the light's direction vector. So adjust the calculations based on that. So here we're checking the W component, and if it is 0, be careful for floating point errors, do directional light calculations. And if it is 1, that means it's not a directional light, it will be some other type of light, either point light or spotlight or something. Fun fact, this is actually how the old OpenGL fixed functionality determined if a light source was a directional light or positional light source and adjusted its lighting based on that. If you now compile the application and fly through the scene, it looks like there is a sun-like light source casting light on all the objects. Can you see that the diffuse and the specular components all react as if there was a light source somewhere in the sky? It'll look something like this. That is source code. Okay, that's it for the directional light. So it's actually pretty simple, pretty straightforward. Let's try to do that. Go to our fragment shader, and here we are calculating our light direction right here. But it is a vector 3. Yeah, the position of this is a vector 3. Let's start from the top. We got the position is no longer necessary when using directional lights. So that means we're going to get rid of them for now. We have a vector 3 direction. And that here we're going to do light direction equals normalized minus light direction. So here we're just inverting it and normalizing it. Okay. Excuse me. Okay, sorry about that. Note that we first negate the light direction. Okay, I already read that. What we need to do is set this uniform to, we need to set the direction now. So we don't have light at position anymore. We're gonna set the direction. This is for multiple objects. I think that should be enough for a single cube. Okay, yeah, this does look like more like a sunlight than a spotlight or a point light. Yeah, looks like the sun that's beaming down, and all the rays are parallel. Okay, that was simple enough. You can also do this W component thing, saying rather than using that, we can do vec4 light vector. Set vec4. We don't have a set vec4. Light vector. And because this is a directional light, we're going to set it to 0. Let's actually first define this function. We're going to need our W component and just pass that in, and that's the one that we're using. Okay, and then here we need to actually use that to determine what type of a light we have. I'm just going to do it at the top here. I'll just copy it from here. If light vector dot 0 and light vector dot 1. Actually, I do need this, and I need the point light as well. Calculation for the point light, yeah, this one. So let's just copy this. Copy this right here, and then based on this, we're either gonna do the point light calculation. That this needs to be defined. So if it's equal to 1, then we're gonna do position light calculation. Otherwise, we can say lighter is equal to minus light dot light vector. Okay, let's call this light vector. Okay, hopefully this will work. I've set it to 0, the W component to 0, so that should work as a direction light. It's not showing up. So it needs to be light dot light vector. Maybe I need to cast it from vec4 to vec3. W vector field selection out of range on line 31. But light vector, okay. When did this become vec3? Oh, when I undo it, cool. Yeah, there's still some errors. Lighter undeclared identifier. I think new. Come on. Constructor not enough. Data provided 0. Undeclared identifier on line 32. Yeah, that's supposed to be okay. I think it's expecting the vec4. So yeah, it messes up our calculations down there. Okay, Control C, Control V. Yeah, it's just saying cannot convert from 4 component vector to 3 component vector. Can just create a vec3 here. But I don't want to normalize 3 times. Okay, let's hope that works. TMP undeclared variable. I mean, you gotta be kidding me. It's so. Yeah. Line 33. I'm declaring it right here. What the flipping hell? And then this. Dude. This is a vec4, and then when we normalize it, shouldn't return a vec4? It's kind of dumb. Anyway, I am just gonna do it like this. So we have the light vector. Let's create a vec3 out of it. Okay, I mean this should work. Nope. Light vector undeclared identifier. Hmm. I have actually no such field in structure. Okay, yeah, because now it shouldn't be light dot here. Selection out of range. Where? 32. What am I doing? Okay. Finally, okay, this is directional light. Let's now try to make it point light. Not sure about that. It's doing something. Don't think it's a point light though. Oh, okay, because the position is different, yeah. Well, it's using a different position, but it is working, didn't throw any errors, so it's fine. If we have to go back, I will do set this to 0 and we're back. Okay, cool. Let's just move on. If you now compile the application and fly through the scene, this is what we see, and that's our directional light. Directional lights are great for global lights that illuminate the entire scene, but we usually also want several point lights scattered throughout the scene. A point light is a light source with a given position somewhere in a world that illuminates in all directions, where the light rays fade out over distance. Think of light bulbs and torches as light casters that act as point lights. Cool. In the earlier chapters, we've been working with a simplistic point light. We had a light source at a given position that scatters light in all directions from the given point light from the given light position. However, the light source we defined simulated light rays that never fade out, thus making it look like the light source is extremely strong. In most 3D applications, we'd like to simulate a light source that only illuminates an area close to the light source and not the entire scene. If you'd add 10 containers to the lighting scene from the previous chapters, you'll notice that the container all the way in the back is lit with the same intensity as the container in front of the light. There is no logic yet that diminishes light over distance. We want the container in the back to only be slightly lit in comparison to the containers close to the light source. That's attenuation. To reduce the intensity of light over distance, light ray travels in general is called attenuation. One way to reduce light intensity over distance is to simply use a linear equation. Such an equation would linearly reduce the light intensity over the distance, thus making sure that objects at a distance are less bright. However, such a linear function tends to look a bit fake. In the real world, lights are generally quite bright standing close by, but the brightness of a light source diminishes quickly at a distance. The remaining light intensity then slowly diminishes over the distance. We are thus in need of a different equation for reducing the light's intensity. Luckily, some smart people already figured this out for us. The following formula calculates an attenuation value based on a fragment's distance to the light source, which we later multiply with the light's intensity vector. Okay, so this is 1 over kcl times d plus k of q and d square. Here d represents the distance from the fragment to the light source, so that's our distance. Then calculate the attenuation value. We define 3 configurable terms. Kc is the constant, kl is a linear term, and kq is a quadratic term. The constant term, we usually keep it at 1, which is mainly there to make sure the denominator never gets smaller than 1, since it would otherwise boost the intensity with certain distances, which is not the effect we are looking for. The linear term is multiplied with the distance value that reduces the intensity in a linear fashion. The quadratic terms is multiplied with the quadrant of the distance and sets a quadratic decrease of intensity for the light source. The quadratic term will be less significant compared to the linear term when the distance is small, but gets much larger as the distance grows. Due to the quadratic term, the light will diminish mostly at a linear fashion until the distance becomes large enough for the quadratic term to surpass the linear term, and then the light intensity will decrease a lot faster. The resulting effect is that the light is quite intense when at close range, but quickly loses its brightness over distance until it eventually loses its brightness at a more slower pace. The following graph shows the effect such an attenuation has over the distance of 100. Okay, you can see that the light has the highest intensity when the distance is small, but as soon as the distance grows, its intensity is significantly reduced and slowly reaches zero intensity at around a distance of 100. This is exactly what we want. Choosing the right values, but at what values do we set these three terms? Setting the right values depending on many factors: the environment, the distance you want light to cover, the type of light, etc. In most cases, it simply is a question of experience and a moderate amount of tweaking. The following table shows some of the values these terms could take to simulate a realistic sort of light source that covers a specific radius or distance. The following column specifies the distance a light will cover with the given terms. These values are good starting points for most lights with courtesy of Augur 3D Wiki. Okay, so these are the distances. You set the constant to 1. Okay, cool. As you can see, the constant Kc is kept at 1 in all cases. The linear term Kl is usually quite small to cover large distances, and the quadratic term Kq is even smaller. Try to experiment a bit with these values to see their effect in your implementation. In our environment, a distance of 32 to 100 is generally enough to make most lights. So we're going to use something between this. Implementing the attenuation. To implement attenuation, we'll be needing 3 extra values in the fragment shader, namely the constant, the linear, and the quadratic term in the equation. These are best stored in the light struct we defined earlier. Note that we need to calculate light direction again using position, as this is a point light as we did in the previous chapter, and not a directional light. So we are just gonna take it back. Don't need this anymore. We're gonna have a position again, and then getting rid of the light vector. Just gonna need this. Don't need this anymore. And we need to add more stuff to our struct. We need a constant. We need linear and quadratic floats, and then we might just set these. Then we set the terms in our application. We want the light to cover a distance of 50, so we'll use the appropriate constant, linear, and quadratic terms from the table. So we have this. That means we just need to set the position again. So we'll set it somewhere here, light position, or light position, yeah, light pulse. Okay. Implementing attenuation in the fragment sheet is relatively straightforward. We simply calculate an attenuation value based on the equation and multiply this with the ambient, diffuse, and specular components. We do need the distance to the light source for the equation to work though. Remember how we can calculate the length of a vector? We could retrieve the distance term by calculating the difference vector between the fragment and the light source and take that resulting vector's length. We can use GLSL's pre-built built-in length function for that purpose. Okay, so it's just calculating the distance from the light and the fragment where we're calculating the light, and then using the attenuation formula, we're using all of these values that will give us the attenuation value, and then we're just going to multiply them with our ambient, diffuse, and specular. That's straightforward enough. Okay, let's actually put all of the lighting stuff at the top. This is our light direction. Okay, so ambient, diffuse, and specular. And then finally, we're just gonna multiply attenuation. Okay, there are some errors. Light direction is an undeclared identifier. On line 34. Yeah, why would you do it like that? Okay, anyway. I'm using it here. Light vector, no such field. 34 again. Actually, just gonna use position again. Well, this gets the length. Yeah, it's fine. Okay, so that's the distance. I might actually need to add more grids so I can actually see the effect of light again. I am using indices, good. Maybe I don't need to Q position. Okay, and there are cubes, and we can actually clearly see the attenuation. The grid in the front receives the most light, and these in the back are not receiving any light. Cool. Okay, so that's our point light. Now what, let's actually try the directional light as well. So we don't need attenuation for now. The distance. We're not gonna do this. Yeah, so this actually looks like directional light coming from this direction. Right. Now for the spotlight. Okay, we can see a point light is thus a light source with a configurable location and attenuation applied to its lighting calculations with another type of lighting for our lighting arsenal. Spotlight. The last type of light we're going to discuss is a spotlight. A spotlight is a light source that is located somewhere in the environment that instead of shooting light rays in all directions, only shoots them in a specific direction. The result is that only the objects within a certain radius of the spotlight's direction are lit and everything else stays dark. A good example of a spotlight would be a street lamp or a flashlight. A spotlight in GLSL is represented by a world space position, a direction, and a cutoff angle that specifies the radius of the spotlight. For each fragment, we calculate if the fragment is between the spotlight's cutoff direction, thus in its cone, and if so, we lit the fragment accordingly. The following image gives us an idea of how the spotlight works. Yeah, we got the light direction vector, which is this red thing here. This black thing is the light direction vector. You have the spot direction, and phi is the angle, the cutoff angle. Theta is the angle to the fragment, between the fragment and the spot direction vector. And then we just need to compare these two. And if theta is less than phi, that means we're going to light that fragment. A flashlight is a spotlight located at the viewer's position and usually aimed straight ahead from the player's perspective. A flashlight is basically a normal spotlight, but with its position and direction continually updated based on the player's position and orientation. So the values we're going to need for the fragment shader are the spotlight's position vector. To calculate the fragment to light's direction vector, the spotlight's direction vector, and the cutoff angle, we can store these values in the light structure. Position, direction, float, cutoff. Okay, let's hold off on these for now. Actually, I'm going to put all of this stuff here so we'll use it. Okay, and finally, let's do the spotlight. Position and direction. We already have the position. Let's do the direction and cutoff. And then we need to set these values. We're going to set these values to the same as the camera's position and the camera's forward vector. So, and then setting the cutoff to 12.5 radians. As you can see, we're not setting an angle for the cutoff value, but calculate the cosine value based on an angle and pass the cosine result to the fragment shader. Okay, GLM radians 12, and then it's doing a cosine on that. The reason for this is that in fragment shader, we're calculating the dot product between light direction and spot direction vector, and the dot product returns a cosine value and not an angle. And we can't directly compare an angle with a cosine value. To get the angle in the shader, we then have to calculate the inverse cosine of a dot product's result, which is an expensive operation. So to save some performance, we calculate the cosine value of a given cut-off angle beforehand and pass this result to the fragment shader. Since both angles are now represented as cosines, we can directly compare between them without expensive operations. Okay, that makes sense. Now what's left to do is calculate the theta value. So calculate the theta value and compare this with the cutoff phi value to determine if we're in or outside the spotlight. So we're going to calculate our theta. Then we're just comparing theta with the light cutoff value, which is also a cosine, and then we can do the lighting calculation. And if not, else use ambient light so scene isn't completely dark outside the spotlight. Okay, it's just gonna do this multiplied with this. Okay, let's try that. So what is our lighting calculations? We first calculate the dot product between the lighter and the negated direction vector. Negate because we want the vector to point towards the light source instead of from. Be sure to normalize all the relevant vectors. You may be wondering, why is there a greater than sign instead of a less than sign if in the if guard? Shouldn't theta be smaller than the light's cutoff value? Yeah, I actually didn't notice that. So this is our theta and this is our phi. Theta should be smaller, and it's checking if theta is greater. Okay. That is right, but don't forget angles are represented as cosine values, and an angle of 0 degrees is represented as a cosine value of 1, while an angle of 90 degrees is represented as a cosine value of 0. Okay, so it essentially flips, as you can see here, and you can now see that the closer the cosine value is to 1, the smaller its angle is. Now it makes sense why theta needs to be larger than the cutoff value. The cutoff value is currently set to an angle cosine of 12.5, which is equal to 0.97. So cosine theta value between 0.97 and 1 would result in the fragment being lit as if inside the spotlight. Running the application results in a spotlight that only lights the fragment that are directly inside the cone of the light. Okay, we need to do the calculations here. Will that be all of it? The diffuse? Not sure. Let's just try this. But even the ambient, it's setting the color here. We're not using this color. What's up? If we do all of it inside this, so we need this. It's going to color is undeclared, cannot convert from 4 to 4 component vector to float. 67. Now let's just look at the source code. Here we have our light direction, normalizing it minus frag, so that's fine. Check if the light is inside the spotlight cone. We're doing that here. We have our theta, and then we're doing the ambient, diffuse, and specular inside here, and also doing the attenuation. Remove attenuation from ambient, as otherwise at large distances light would be darker inside than outside the spotlight due to ambient term in the else branch. Okay, so he's taken all of this, put it here. Here in the else branch, okay, he's setting the frag color directly. Use ambient light so scene isn't completely dark outside the spotlight. So this is our result. And it's not doing the ambient. Still some error. Attenuation is undeclared on line 67. Okay, I did comment that out. Okay, so for spotlight and point light, we need this attenuation value. Constant linear. Okay, so we're gonna need all of that. Let's enable it here as well. Okay, and that's our spotlight. Right. Smooth or soft edges. To create the effect of a smoothly edged spotlight, we want to simulate a spotlight having an inner and an outer cone. We can set the inner cone as the cone defined in the previous section, but we also want an outer cone that gradually dims the light from the inner to the edge of the outer cone. To create an outer cone, we simply define another cosine value that represents the angle between the spotlight's direction vector and the outer cone's vector equal to its radius. Then if a fragment is between the inner and the outer cone, we should calculate an intensity value between 0 and 1. If the fragment is inside the inner cone, its intensity is equal to 1 and 0 if the fragment is outside the outer cone. We can calculate such a value using the following equation. Here epsilon is the cosine difference between the inner phi and outer cone. What is this, lambda? No. The resulting I value is then the intensity of the spotlight at the current fragment. So we have two angles, the inner degrees in degrees. Okay, so this angle and this angle. So inner radius and outer radius. This is our outer cutoff, this is our inner cutoff, and this is the angle of the fragment. As you can see, we're basically interpolating between the outer cosine and the inner cosine based on the theta value. So if you still don't really see what's going on, don't worry. You can simply take the formula for Grant and return here when you're much older and wiser. We can now have an intensity value that's either negative when outside the spotlight, higher than the one when inside the inner cone, and somewhere in between around the edges if we properly clamp the values. We don't need an if else in the fragment shader anymore, and we can simply multiply the light component with the calculated intensity value. Okay. That's inner cutoff minus the outer cutoff. And this is theta in degrees. 35 minus the outer angle. Okay, so that's a theta epsilon. Oh, this is epsilon. This is epsilon. And of intensity. We leave ambient unaffected, so we always have a little light. Here, theta is the dot product of light direction and the normalized form of light dot direction. Let me just check. This is our light position at frag position, so it's that vector, and that we're doing a dot product on that, and that is our angle, cool. And then epsilon is light cutoff, light dot cutoff minus light dot outer cutoff, so these two, that will be our epsilon, this value, okay. And then we're gonna clamp theta minus light dot outer cutoff, so that's this, and we're dividing by epsilon value that we calculated, and we're clamping it between 0 and 1, so that's our intensity. This sort of makes sense, I guess. Diffuse and specular. So it's saying we don't need the if block anymore, and the else block. It's doing theta epsilon intensity. I already have theta. Yeah, but it's not taking attenuation into account, so we'll have to do that as well. Okay, let's do this for now. Yeah, I think we need to set these values first. Okay. I don't know, let's just look at the code. This chapter was much more intense than I expected. Position, direction, cutoff, and outer cutoff. We need to set these cutoff values actually. Just use direction like this. Here, yes, we have our ambient. Then we have our diffuse and specular. Okay, so then we have a spotlight calculation, theta epsilon intensity, and then multiplying that intensity with diffuse and specular here, since we do need attenuation at the end. Okay, and then distance and attenuation right here. This is kind of weird. Okay, I think the normals are flipped on this one. Maybe I need to set some values. Okay, yeah, this is much better. Yeah, but this is not lighting properly. Anyway, so that's the spotlight. That's much better. Play around with the inner and outer cutoff angles and try to create a spotlight that better suits your needs. You can find the source code of the application here. Such a flashlight spotlight type of lamp is perfect for horror games and combined with the directional and bright light, the environment will really start to light up. Experimenting with all the different light types and their fragment shaders, try inverting some vectors and or using less than or greater than and try to explain the different visual outcomes. Okay, yep, that's it for this chapter, Lightcasters. Stream has been going on for almost 1 hour and 5 minutes. So I think that brings today's stream to an end. If you're watching on Twitch, you can actually go to YouTube. Let me just grab the link. Twitch.tv/Goldstrom. And you can get the link to my YouTube right here. Here you can see the playlist of all the previous videos, all the previous 9 days, and then I'll also upload this one. So you can actually follow along while I'm learning OpenGL. You can also learn along with me. And if you're watching this on YouTube, you can I actually stream on Twitch every weekend, so close to 1 hour stream, which I then subsequently upload on YouTube. So if you want to catch me live, you can catch me on twitch.tv/Codestrum. Okay, that's it for this stream. Goodbye.